All right, so we are now recording. So this is our error correction model. Maybe I need to restate for the purposes of recording it, to restate the long run equation. The long run equation is yt is equal to alpha 0 plus alpha 1 plus alpha 2 x1t, then alpha 2 x2t, x2t plus the white noise error term. So yt is given by alpha 0, alpha 1 x1t, then plus alpha 2 x2t plus an error correction term. And like I said, this is the constant. This is the coefficient of x1t, alpha 1, and alpha 2 is the coefficient of x2t. And I said alpha 1 and the alpha 2 are the long run parameters. So alpha 1 and alpha 2 are the long run parameters. The long run parameters. Okay. Then I went on to say that before you apply the co-integration and error correction methodology, you are supposed to test all your variables for non-stationarity. And all your variables are supposed to be non-stationary in levels. They are supposed to be non-stationary in levels, and they should become stationary after first differencing. And the other property which I mentioned is that those variables included in your long run regression equation, your yt, x1t, and x2t, are supposed to be co-integrated for you to be able to specify and estimate the error correction model. They are supposed to be co-integrated. So how do we test for co-integration? I said to test for co-integration, you need to generate the errors from your long-run equation. And those errors are supposed to be lagged ones. And this is the equation that helps you to generate the errors which are lagged ones, which is given by yt minus 1. That is yt lagged ones minus alpha 0 minus alpha 1, x1t lagged ones minus alpha 2, x2t lagged ones. So this is what gives you the errors. And I said it is these errors that you use to test for co-integration. And I said to test for co-integration, you are supposed to use either the augmented Dickey-Fuller test or the Phillips-Perron test using a regression model where you neither have a constant and a trend. So the model that you use to test for co-integration is supposed not to have a constant and a trend. So you are testing at none. When you are in E-views, you are testing at none. So if you establish that the square integration amongst the variables included in the long-run equation, that is the passport you need to specify and estimate the error correction model. And I said the error correction model is specified in first differences of the variables. The first difference of yt plus beta 0, and I said the parameters have to change, because the parameters in this equation are different from the parameters in the short-run equation or the error correction model. Short-run or error correction model, ECM. ECM. So if it is written as ECM, it means error correction model. So this is the short-run error correction model that we are specifying here. ECT means error correction term, which represents the errors generated from the long-run equation. So I said this is the constant for the short-run error correction model. And this is the short-run parameter. Beta 1 is a short-run parameter in this error correction model. Beta 2 is also another short-run parameter in this error correction model. And beta 3 is the long-run parameter, which is the coefficient of the error correction term, which we said is the what? Is the one that gives us information about the speed of adjustment of our dependent variable yt towards its long-run equilibrium, the speed of adjustment of yt towards its long-run equilibrium. And I said that this beta 3 is supposed to be negative, is supposed to be negative and significant for it to have economic meaning, right? It's supposed to be negative and significant for it to have economic meaning, right? So the beta 3, the coefficient of the error correction term, is supposed to be negative and significant for it to have economic meaning. If it is, the other thing that I can add here is that beta 3 must actually lie between -1. It must lie between -1. This is beta 3. It must lie between -1 and 0. -1 and 0, right? It must lie between -1 and 0. If it is beyond these limits, then the results that we get are explosive. They are explosive. In such a situation, it could be that there's something wrong with your model specification. So you need to go back to the drawing board and start again. Because for you to estimate the error correction model, you have already established that there is a long-run equilibrium relationship amongst your variables. If you then find the beta 3 parameter, which is beyond these limits of -1 to 0, then the results that you've got are explosive, and you need to go back to the drawing board and start afresh so that you adjust your model, adjust your specification, maybe you may also need to what? To change your variables. If they were not logged, you may need to transform them to logs, to transform the logs for you to end up getting the results that are in line with the fact that your variables are co-integrated, right? So I hope that is clear. If there is something that is not clear, please, you can always ask. You can always ask. Right, so I hope you've understood everything that I've explained here. Now, the next thing that I want us to do is to just move on. Move on. So, in the practical session that we are going to do, the steps that we are going to follow, when using co-integration and error correction modeling, the first step is to estimate the long-run equation. That is before the long-run equation, you test your variables for unit roots, and you must establish that all of them are integrated of order 1. So that's the first step. Once you are done with that, the next step is to estimate the long-run equation. You estimate the long-run equation, and then test the errors you generate from the long-run equation for co-integration. If you find that the variables are co-integrated, the variables in the long-run equation are co-integrated, the next thing you do is to specify and estimate the error correction model. And the error correction model, like I said, is 2 parts. It is the short-run part, where we have short-run parameters, and the long-run part, where we have ECT lagged ones and its coefficient. That's the long run part. Then after that, the last thing you do is to do some diagnostic tests. And under the diagnostic tests, there are some additional things that I'm going to do, which we did not discuss in the theoretical lecture. So this is why I always say it's important to attend both sessions. Right, so I'm going to unshare this and share the data that we are going to use. And by the way, you requested that I share with you the data that we are going to be using in the data that we are going to be using in the practical sessions. So I've shared this data that we are going to use today. I've shared it with you on e-learning. If you check, the data is now there. And it's this data that we are going to use in this session. Now, what I'm going to do, we are going to start from scratch, just like we did the other time. The first thing you do is to copy your variables. You highlight all your variables, which are running from 1990 to 2023. You copy your variables like that. Then you right-click on the highlighted, one of the highlighted cells and copy. And that moving line outside the copied data shows is being copied. It has been copied. So let's now minimize this. Are you seeing what I'm showing? Did you see the Excel data?
Yes, sir.
Yes, sir.
Okay. If you don't see things, please tell me in time before I go. Then we go on. We now want to open our eViews work file. This is the eViews work file. If you open it, we are going to create a new eViews work file. So we just click create new eViews work file. I'm sure you should be familiar with this interface. And we are going to use annual data running from 1990 to 2023. So this is our data. And we are going to call it practice work file 2024. Practice work file 2024. Okay, fine. This is what comes up with 34 observations. Now, the next thing is you click on quick. Then you go to empty group. Click on that. This is what comes up. You put your cursor in the cell against 1990, right? Then you hit the upward arrow on your keyboard once. You do that, you create a row above 1990, right? That one. And I said the importance of this row is that the names of the variables are going to appear in that row. They will appear in that row and also in the row which is in blue above that first row that we've created. So that is where the names of the variables are going to appear. But the names that you will be able to use are the ones in the white row, this row here. This row, the first row that we've just created. Those are the ones that you will be able to copy. You cannot copy the names that are on the blue cells. Okay, so that's the importance of creating that additional row. So the next thing that we do is to right-click in this cell, this blank cell, this first blank cell, right-click and paste. Right-click and paste. There's something wrong. Okay, I hope I will be able to correct it. Whatever is wrong with there. Let's see. All right. Okay, I clicked in it. I think I did done something. I'd put, you see, what's happening in that cell. You need to remove that. You don't need that in that cell. Okay, you need it. Okay, let me start over. Was I don't want to create problems. Let me delete this and delete that as well. No, right. So I go back, new work file. We are there. Then is annual data, 1990 up to 2023. So I called this what practice work file 2024. I hope it will accept the name. Yes, it is accepted. Practice work file 2024. Then we go to quick empty group. Like I said, you hit the upward arrow when your cursor in that cell, create that additional row. Then you just right click in that cell and paste. And these are the variables that we have in our data. So I can name this group 1 to keep the data, and the variables are there. So this is what you do to copy your data from Excel to eViews. Now, the next thing that I want us to do, this is another first step that you should not forget, is to change your variables to logs. And you can only change your variables to logs if all of them, if some big numbers that are greater than, that are positive, greater than 0, right? Greater than 0. You can only take logs for such variables. So let me open the group once again so that you see what I'm saying. If you open the group, I'm sure you can see all our numbers here are positive. All of them are positive. There is no figure that is negative. You cannot take logs for negative figures. So all our numbers are positive, which means we can take logs for all these 4 variables. We can take logs for all our 4 variables. So let's do that. Let's do that. Remember, I said the formula that we use to convert our variables to logs. The name that you want to give to your variable, for example, LN GDP, this is the name that I want to give to the new variable I'm creating. LN GDP is equal to, this is the formula, log GDP, log GDP, log GDP, close bracket, open bracket and close bracket. So this is the formula that we use to convert the GDP variable to logs. And you can do the same with all the other variables. The formula is the same. You just type in log LN PCE is equal to log in brackets PCE. That's it. So that's the formula. So using this formula, we want to generate the logs of these variables. Now, for you to do that, you have to go to generate, this generate here, GENR. It means generate. So this is where you generate your variables. And if you want to multiply certain variables, this is where you come to multiply the variables so that you come up with one variable. Or if you want to change to use a formula for example, you want to add PCE to PDI to come up with one variable, that's where you go, right? I'm sure we'll do that as we go. So let's generate the logs of our variables. So the first one is LN GDP is equal to log in brackets GDP. So that's the first variable. We've created what? LN, and this LN is already here. It means we've created the variable in logs. And we will look at the group in logs as well. Then we generate the next one. Len PCE. PCE is equal to log PCE. PCE. Len PCE. It doesn't matter whether you use the capital letters or small letters, it's the same. So we have our len PCE. Then you go to the next one, len PDI, LN PDI is equal to log PDI, close bracket, with our variable. Then we go to the last one, what? Len dividend, LN div is equal to log log div, log div. So that's it. We have all our variables in logs. And we can open a group for these variables in logs so that you see them in one window. So we start with our GDP, PCE, PDI, and the div. What has happened? Start with the GDP, then PCE, PDI, and that. Right click on anyone, then open as a group. I'm sure you can see the figures are now much, much smaller than the figures that were in thousands that we had earlier. So these are the figures in logs. These are the figures in logs. And I'm sure if you use these to draw your graph, it will be slightly different from the one that we had last time. So I'm going to name this group 2, right? Now, I'm going to use these 4 variables. I'm going to graph them. This is the what? This is the informal test for unit roots, if you still remember. If you graph them and see that they are trending upwards, then you know that they are not stationary. So click OK. This is what we said. We are going to try and draw them in a single graph. Since the figures are small, I'm sure all the graphs will appear in a single graph. Click OK. Right. I'm sure you can see all our variables are shown. All our variables are shown. Now, if you look closely, you can see that the blue one is GDP, is trending upwards. Even the next one, consumption, is trending upwards. Even this one, the next one, is trending upwards. I'm sure you can see that. Only the last one is the one that appears not to be trending upwards, right? I'm sure you can see that. Which means if we test this last one, for stationarity, is likely to be stationary in levels. It's likely to be stationary in levels. And if it is stationary in levels, it means we cannot include it in our co-integration and error correction modeling. So let's do that. So this is the first step. I can save this. I can save this. Let me save this.
Sorry, sir. Can you show us again?
Show you what?
How to go to the graph. We were busy saving the logs.
What do you want me to show you?
How you got to these graphs?
How I got the graphs. Okay. All right. All right, let me close the graph. Right, what I said is you have your 4 variables. So you pick them in the order in which you want them to appear, you pick the 4 variables. That's it. Then the next thing you do is you go to quick. Then you go to graph. Then you click OK. And here, you want to draw them in a single graph, right? So it's the one that is chosen. You can draw them in stack. They can be stacked in a single graph or in multiple graphs. Multiple graphs, it means each graph, each variable will appear in its own graph. That is the multiple graphs. So I picked the first one and then clicked OK. This is what gave us this, right? So I've already saved this.
Okay, thank you.
Yes, if you want it in a single graphs, you just go to quick graph, OK. Then you pick multiple graphs, click OK, right? As you can see, it's now very clear that GDP is upward trending, PCE is upward trending, this one is upward trending, but this dividend, we are not very sure because it appears to have an upward trend and then a downward trend. It appears to be behaving that way. So these are our 4 variables. Now the next thing, you can also name this. And I would urge you to listen to the first tutorial we did, because there are some things that I did for the years to appear nicely and also for the graphs themselves to appear nice. There's something that I explained in that lecture. So you have to listen to that one as well. All right, so we are done with this. The next thing, let's try to just verify if the variables are integrated with order 1. Let's do our GDP, variable. GDP variable. I will open the GDP variable. Then we test it for unit roots using the augmented Dickey-Flower test at none. So we go to view, unit root test, standard unit root test at none. So you pick none, right? You are testing the variable in levels at none. That is the test that you do. And if this test shows that the variable is stationary in levels, if the variable is stationary in levels, then it doesn't have a what? It doesn't need to be different if it is stationary after. No. I think I'm missing up things. Why are you not telling me? Here we are just doing the normal unit root test. So we need to do the 3 tests in level, intercept, trend, and none for this GDP variables. We want to see whether it's integrated of order 1. So let's quickly do that. We do this. What is this telling us? It's non-stationary. It's non-stationary because the calculated t-statistic is more negative than. Is it more negative than all this?
No, sir.
What is it? Is it more positive? Is it greater than all these ones? Right. So it's
Yes,
more.
sir, it's
It's
more.
positive. It's greater than all these critical values. If you look at the p-value, it's also telling us that the variable is non-stationary in levels. Then we go to the next test using trend. What is this telling us? It's telling us that GDP is what?
More negative.
This one is telling us that the variable is stationary in levels. Can you see that? It's telling us it's stationary in levels. Then we go to the next test. Next test at none in levels is not stationary, which means 2 out of the 3 tests that we have done in levels are showing us that GDP is non-stationary. 2 out of 3. And I told you that you go with the majority, but let's leave it at that for now. Now let's do the test in first differences. Do the test in first differences using the model with intercept. The first difference of GDP is stationary in levels, right? The first difference of GDP is stationary. Then we go to the model with trend and intercept. Is also telling us that the first difference of GDP is stationary. We go to the model with none. It's also telling us that the first difference of GDP is stationary at 5% level of significance. If you use the probability, 5%, and this 2 minus 2.4 is lying between 5% and 1%, which means it's stationary at what? 5%. Right, so we've confirmed that GDP is integrated of order 1. So our GDP is integrated, and you must be able to write this integrated of order 1. It needs to be first difference to become stationary. So we are done with that test. Let's quickly go to the next test, PCE. PCE, we do the test unit root standard in level first. What is this telling us quickly? Non-stationary. Variable is not stationary because the p-value is greater than 5%. We go to the next test, trend and intercept. It's telling us that the variable is stationary at 5% level of significance. Right? We do the third test. We do the third test at none. It's telling us that the variable is non-stationary. So 2 out of the 3 tests are telling us that the variable is non-stationary, which means we go with the majority, just like we did when we used the augmented Dickey-Fuller test. We go with the majority, so the variable is non-stationary. Now, if we repeat the test in the first differences, you click first differences, then you click intercept. The variable is now stationary at 1% level of significance. The first difference of PCE is stationary at 1% level of significance. Then you go to the next test with the intercept and trend. The variable is stationary at also 1% level of significance. You repeat the test at none. The variable is stationary at 5% level of significance. This is lying between 1% and 5%. So we conclude that PCE is integrated of order. PCE is integrated of order 1. PCE is integrated of order 1. Then we go to the next one. Let's go to the next one. This is very important what we are doing, because remember we said you can only use co-integration in error correction modeling if all your variables are integrated of order 1, right? If all your variables are integrated of order 1, that's when you can use co-integration in error correction modeling. So this exercise is very important. Then we do the next one, PDI. Open PDI, then you go to view. Let's do the test. Unit root in levels, intercept, right? It's showing us that the variable is non-stationary. The second test, trend and intercept in levels, the variable is non-stationary once again. The third test, at none, click that. The variable is non-stationary. So all the 3 tests are unanimous in the fact that the variable PDI is non-stationary in levels. So you repeat the test in first differences. repeat the first differences. You go to first difference, intercept, okay. As you can see, the variable is now stationary at 1%. The first difference of PDI is stationary at 1%. You repeat the test at using a model with constant and trend is also stationary at the first difference of PDI is stationary at 1% level of significance. Then you repeat the test using this one at none, same applies. It's stationary at 1%, which means we can conclude that PDI is integrated of order 1. It's integrated of order 1. This one is also integrated of order 1. It's integrated of order 1. Right. Then we do the one. We do the last one. P lin div. So we open that variable. Then let's do the test. Right. We are doing the test in levels. What is it telling us? The variable is stationary in levels at 5%. I'm sure you can see that. Then using the model, it's trend, using trend and intercept, the variable is stationary in levels at 5%. Then we repeat the test again at none. The variable is non-stationary. I'm sure you can see that. So two tests are telling us that it's stationary. One test is telling us that it's non-stationary. So we can repeat this test using the Phillips-Perron test. We can repeat this test using the Phillips-Perron test just to confirm so that we make the correct decision. Did we do it in first difference? No, there's no need. So let's do it in using the Phillips-Perron. We want to confirm whether it's stationary in levels or not. So let's do it in using Phillips-Perron intercept. It's telling us that the variable is non-stationary. I'm sure you can see that. Then you go to the next one. Phillips-Perron trend and intercept is also telling us that the variable is non-stationary. Because the Phillips-Perron test is more powerful than the augmented Dickey-Fuller test. This is what I tried to explain when we discussed the second chapter, that the Phillips-Perron is more powerful than the augmented Dickey-Fuller test and the Dickey-Fuller test, because it uses non-parametric tests to determine the parameters. And it is also important in that it resolves the problem of autocorrelation and heteroscedasticity. That is the other thing that I mentioned. So it's more powerful. Maybe that's the reason why it's giving us these results. Then testing at none, what does it tell us? It's also telling us that the variable is non-stationary in levels, which means using the Phillips-Perron, all the three tests are telling us that the variable is non-stationary. Using the augmented Dickey-Fuller test, two of the tests are saying is stationary, and one test is saying is non-stationary. So adding all of them together, the 6 tests, 4 of the tests are saying it's non-stationary, and the 2 are saying it's stationary, which means we go with the majority that the variable is non-stationary. Are we together on that?
Yes, sir.
All right. So great. So it means this variable is also integrated of, tell me the answer.
Order 1.
Yes. So div is also integrated of order 1. It's also integrated of order 1. So all our variables are integrated of order 1, right? Now, the next thing that we need to do is to run a long-run model. Now, using that long-run model, we are going to generate some errors. which we are going to use to test for co-integration amongst these variables. So the model that we want to estimate, let me just specify it before we proceed. So the model that we want to estimate is this model, lean GDP, GDP, T plus, oh, not plus, is equal to, is equal to alpha 0 plus alpha 1 PCE, alpha 1 PCE plus alpha 2 PDI, PCET, this is PDIT, T plus alpha 3 div. Remember, our variables are in logs, so don't forget to put the ln, because our variables are in logs. Put the ln div plus a white noise error term with the properties that we discussed. So this is the model that we want to estimate, and this is our long run model. GDP is the dependent variable, which is explained by personal consumption expenditure, personal disposable income, and dividends. That is what explains our GDP. Okay? So the parameters alpha 1, alpha 2, and alpha 3 are the long run parameters in this long run equation. So the other thing that I think I should mention here is that the long run parameters for all our 3 independent variables are supposed to be greater than the short run parameters of these 3 variables when we specify an error correction model. So that is how these variables, these parameters are supposed to relate. The parameters for the long run equation are supposed to be greater than the parameters for the short run equation. It's something that you need to remember. All right. So let's now go on to we have established that all our variables are integrated of order 1, which means we can use them in our co-integration and error correction modeling. So the first thing that I want us to do is to estimate the long run equation. When picking your variables, the dependent variable is the one that you pick first. So you pick your dependent variable, then you use the control key and your mouse, you press the control key down, then you pick PCE, pick PDI, PCE, PDI, and then pick a dividend in that order. So that is the order in which you want the variables to appear in your regression equation. Then you put your cursor in any one of those cells that are highlighted, right click, and open as equation. Open as equation. Click that. Then you see the variables are in the order that I picked them. In the work file, GDP, we want the constant to come after GDP, so we'll put our constant there and remove it from the end of the equation. Then with PCE, PDI, and dividend is our independent variables. Those are the independent variables. So if we estimate this equation, and the method that is chosen by default is the least squares. This is the ordinary least squares method. And it's also the method that is used when using nonlinear LS and the AMA, the one that we discussed the other day. Remember, we talked about the AMA PQ. AMA PQ, which is made up of the AR and MA together in one model. So we use least squares to estimate AMA, this NLS and LS, ordinary least squares. So if I click OK, this is the estimation. These are our results. And if you look at these results, we have the constant. This is the standard errors. They are all very small, meaning that the model that we have estimated here is efficient, right? The standard errors are very small. The t-values for the first three, for the constant, PCE, and PDI are greater than 2. Remember, I said 2 is the rule of thumb that we use. If your t-values are greater than 2, then it's most likely that that variable is significant in explaining the dependent variable. So our dependent variable is that GDP. That is our dependent variable. This GDP, this is our dependent variable. And these are our standard errors, which are very small. Then the t-values. If you look at the probabilities, the constant is significant at 1% level of significance. PCE is significant in explaining GDP at 1% level of significance. Then you go to PDI, is also significant at 1% in explaining GDP. If you go to dividend, it's not significant in explaining GDP. In our first practical lecture, I said you can test whether dividend is a variable that we should maintain in this model by looking at the adjusted R squared. If you remove dividend and the R squared, adjusted R squared increases, then it means dividend is a what? Is a redundant variable. We call it a redundant variable. But if we remove dividend and the adjusted R squared becomes smaller, it means the dividend should be included in this model, right? It must be included in this model, right? So we are not going to do all those other, okay, maybe we can do them, the diagnostic tests, so that you see the difference between this and what the error correction model will show us, right? So look at adjusted R squared. I want you to write down this figure for adjusted R squared, 0.99098. Write it down, because we want to compare it when we remove a dividend to see whether dividend is a redundant variable or not. Then the other thing is, I want you to check the F statistic. What is it telling us? What is the F statistic telling us? This is the calculated F statistic and its probability. What is it telling us? The calculated F statistic and its probability. Please, you must participate. If I ask a question, you do not take two minutes because you are listening and following. You just provide me the answer. We did this. We said the F statistic give us what? It tells us whether these three independent variables jointly influence the dependent variable. And if the p-value is 0.000 and the F statistic is 12 point something, 12,186. What is this telling us? What is this telling us?
Sir, is it that they are jointly significant in explaining the dependent variable?
At what percentage? At what level of significance?
1%.
Correct, 1%. Because it's 0.000, which is less than 1%. So it's 1%. Then the next thing that I want us to do, we said in our lectures, as we do these things, my advice to you is before we do each lecture, you just browse through your notes to revise this thing, because I don't think the notes that I'm giving you are too much. They are not too many. It's something that you can browse through before coming for the lecture. Or once a week, just create time to browse through the lecture so that you don't forget. In the lectures, I said that if R squared is greater than DW statistic, we said this is the rule of thumb, which gives us the information that the results that we found are superfluous or nonsensical, right? But in this case, our adjusted R squared is smaller than the DW, which suggests that the results may not be superfluous. But in spite of that, our results suffer from the problem of autocorrelation, because our DW statistic is not lying between 1.7 and DW. Remember, I said this is the rule of thumb, and 2.3, right? It's not lying between this and that. So still, our model suffers from autocorrelation. There is autocorrelation, which means these results cannot be trusted. They cannot be trusted, right? Since our model is showing that it is autocorrelation. So, having said that, this is the interpretation that I want to give here, nothing else. Maybe if we can look at the coefficient of PCE. What this coefficient is telling us is that a 1% increase in PCE, in the lean PCE, will lead to a 0.987% increase in GDP. A 1% increase in PCE will lead to a 0.897% increase in GDP. Ceteris paribus. That's how you can interpret that. And you can interpret all the other variables in the same manner. So let me not waste time by hammering on that, because I want to introduce some new things. Okay. So this is our long-run equation. And using the results that we have found here, you can also summarize your long-run equation by using these results, right? It's something that you can do. So your lean GDP is equal to, what is the constant? 0.94. 0.94, that is the constant, plus the coefficient of PCE is 0.90. We can say 0.90 to the nearest.
937.
0.99 what?
The
I said
constant is
PCE
0.93.
to the nearest. Oh, 93, yes, you are right. Thanks for that. It's 0.93. Thanks for the correction. Right. So the next one is 0.90. 90 PCE. So this is your long-run equation, the estimated long-run equation, plus the next one is 0.05.
Sorry, sir. Should we
0.05.
specify learn PCE? Or should we just put PCE?
I'm not getting what you are saying.
Should we put learn PCE or just PCE
You have to
in
put
the
lean
equation?
PCE because that is what is in your model. You have to put that. So the next one will be 0.05. 0.05. Once again, it's lean. What? PDI. You should not forget that. I have the luxury of making mistakes, but in your case, you can't make mistakes. You have to be accurate. That's why I always say, if I make a mistake, please correct me immediately. Because if you copy the wrong things, then you are the ones who write the wrong things in the test and exam. Then the next one is 0.001. 0.001. A lean diff. So this is our estimated long-run equation. If you want to rewrite it, this is how you can rewrite it. And normally, if you rewrite it this way, then you have to put the standard errors. It's normal practice to put the standard errors or the t statistics below each one of them. You write the t statistics. The t statistics here below each variable, below each coefficient. You put the t statistic. Put another t statistic for this one, and t for that one. So if you write it this way, that's the way you do it, which means the first t statistic for that will be 11.39 or 11.47. That's it. So the next step, I want us to quickly check the diagnostic test. And I want you to write down the information, the conclusion that we are getting for each diagnostic test, because we want to compare it with the error correction model that we are going to estimate. So I will remove this information that I've added here. That's it. So let's do the diagnostics. Now the diagnostics, the first thing that we will do is to test these results using the Q statistics, the correlogram Q statistics. There is autocorrelation if the probability values are less than 5%. Using is another method that you use to test for autocorrelation, the correlogram. So correlogram Q statistics, let's do that and see what you get. These are the correlogram Q statistics. Can you see that? The probability values are less than 5%. Can you see that? They are less
Yes,
than
sir.
5%, which means there is autocorrelation. In other words, the null hypothesis that we are testing here, just like we did previously, the null hypothesis is that there is no autocorrelation. No autocorrelation, no autocorrelation, no autocorrelation against the alternative that there is autocorrelation. Alternative that there is autocorrelation. And our decision rule, if the p-values are greater than 5%, we fail to reject the null hypothesis. That is how we put it in our lectures, autocorrelation. So here, there is autocorrelation using this method, right? Because the p-values are smaller than 5%. Let's go to the next test. I hope you've taken note of that. There is autocorrelation. I said summarize that on a piece of paper. Of course, I'm sure I will remember as we do. And I don't know if you are going to remember the way I'm remembering. The way I remember, because I've taught myself to remember things. Then the residual, we go to, let's now do the Bruch-Godfrey serial LM test to see if it confirms what we found. Bruch-Godfrey serial correlation LM test. What is it telling us? The hypothesis is the same. There's no autocorrelation and there is autocorrelation. What is this test telling us? We fail to reject the null hypothesis if the p-value is greater than 5%. What is the conclusion here?
It's more
Using
than
the
5%.
F-test, yeah?
It's more than 5%.
Meaning what?
The probability. It has autocorrelation.
Correct. That is what I want to hear. There is autocorrelation. So this test is confirming the correlogram Q test that we used first. It's actually confirming that there is autocorrelation, because that is what we found using the correlogram. Then there is autocorrelation using both tests. Let's go to the next one. Histogram normality is telling us that the Jagg-Berer calculated test statistic is 0.45 and the probability is 0.79. What is our conclusion here? The null hypothesis is the residuals from the estimated model are normally distributed against the alternative that the residuals from the estimated regression equation are not normally distributed. What is our conclusion? The residuals are what?
They are not normally distributed.
Is that correct? For your information, I did not bring questions in the test that required you to interpret this, but I could have done it. The p-value is greater than 5%. Our null hypothesis, you must understand this stuff without any shadow of doubt. Otherwise, there will be gnashing of teeth in the final examination, right? You must understand this perfectly well. That's what I'm trying to emphasize. So here we are saying residuals are normally distributed residuals. That is the null hypothesis. Residuals are normal. Are normal. And the alternative is the residuals are not normally distributed. And we said if the p-value is greater than 5%, we fail to reject the null hypothesis. So the residuals are normally distributed. The residuals are normally distributed. We go to the next test. We go to the what? The heteroscedasticity test. I said using the heteroscedasticity test, you can do 2-3 tests. But in this case, we are just going to do one test. We are using the H test. What is this telling us? The null hypothesis is residuals are homoscedastic. What is our conclusion, please? We need to
we
move
fail
fast.
to reject HO. They are homoscedastic.
Yes, residuals are homoscedastic. And the alternative hypothesis is that they are heteroscedastic. So this is homoscedastic. Homoscedastic, right? So the residuals are homoscedastic. Fine. So the only test that is given us something that we don't want is the autocorrelation test. The other tests are giving us what we want. Then we go to the next test. What? We've done all this. We go to the stability tests. We choose Ram's reset test for model specification, whose null hypothesis is, what is the null hypothesis for the Ram's reset test?
Model is correctly specified. Or
The model is correctly specified against the alternative that the model is not correctly specified. And using these three tests, all these three tests, the T statistic, F statistic, but I encourage you to use the F statistic, right? That's the one you are supposed to use. Its calculated test statistic is 0.377549, and its probability is 0.5437. So the probability is greater than 5%. What is our conclusion?
we
The
failed to
model
detect.
is correctly specified, right? The model is correctly specified. So we are done with that. We go to the next test, the last one. The Kusum test. The blow line lies entirely within the 95% confidence intervals. The null hypothesis in this case is the parameters in the regression equation are not stable against the alternative that the parameters in the regression equation are stable. So if the p-value is smaller than 5%, that is if the blue line lies between the upper and the lower bound, the 95% confidence intervals, it means it's lying within the 5% confidence interval. So what this means is that the parameters, if the blue line is within those 95% confidence, the parameters in our regression equation are stable. That is the conclusion we come to. So we reject the null hypothesis and accept the alternative. That is our conclusion for this one. Now, the test can be repeated by using the Kusum of squares test. And the interpretation is the same. So, can you see what we've done here? All the diagnostic tests that we've done are giving us the results which show that the model that we've estimated is good, except for the autocorrelation test. But the autocorrelation test is one of those critical tests that needs to be satisfied for us to say our model is good. So we cannot say our model is good when there is autocorrelation in our model. So there is a problem. Right. So let's now move on. The next thing that I want us to do, if you want to go back to the results, just estimate, go back to the results. We are back to the results window. They are there. So the next thing that I want us to do, this is a very important step. I want to show you how you generate the errors that you can use in your error correction model, which errors you are also going to use to test for co-integration amongst the variables that you have included in your long-run equation. So, to test the errors, to generate the errors from this estimated model, you go to proc. You go to proc. These are steps that you have to know. You go to proc, then you go to make residual series, make residual variable. That is what this means. Make residual variable. Then you click that, and it's saying the residual type is ordinary. And we want to give this residual a name that we will remember. The default name that is given here is resid01. We don't want the default name. We want to call it ECT, error correction term. We want to call it ECT or error correction term. That is the name that we want to give to this variable. So click OK. So this is our variable, the error correction term. As you can see, these are the errors that are associated with each year, right? From this estimated equation. So this is the difference between the trend line and each observation, right? This is what we have done. So we've generated the errors. These are the errors that we need to test for co-integration. What did we say our our what? Our null hypothesis for co-integration test. What is the null hypothesis for co-integration test? Co-integration test. That is what we are doing now. Co-integration test. Co-integration test. Co-integration test. The null hypothesis we said is what? H0. What did we say the null hypothesis is? You guys, you are very discouraging. I get very discouraged if you are not participating. These are things that we've done. If I ask a question, just answer so that we go on. You must not be afraid of making a mistake. We are here to learn. I also make mistakes. You make mistakes. Even if you give a wrong answer, we are not going to crucify you because you've given a wrong answer. We are all here to learn. So don't look at each other, please. Just give the answer. Even if it's wrong, that's part of learning. I will correct you and then we move on. Okay? So the null hypothesis is what?
There is no co-integration.
Yeah, but I need the answer very fast. Okay, thank you. There is no co-integration, right? The alternative is there is co-integration. There is co-integration. What is the decision rule? What is the decision rule for such a hypothesis?
Reject H naught if p-value is less than 5%.
Correct. Reject H naught if p-value is less than 5%. Correct. That is very correct. So our decision rule, reject H0 when p-value is less than 5%. Correct. So this is everything we need. And I said, let me reiterate, this is something that I've mentioned over and over again. To test for co-integration, it's like we are testing the errors we have generated. We are testing the unit roots for the errors that we've generated using an augmented Dickey-Fuller test equation or a Phillips-Perron test equation without a constant and a trend. So if we find that the errors, are stationary in levels, if the errors are stationary in levels, then there is co-integration. There is co-integration. If the errors are stationary in levels, there is co-integration, which means there is a long-run economic relationship amongst the variables included in the long-run equation. And that is what allows us to specify and estimate an error correction model. So we are going to test for co-integration using both the Phillips-Perron and the augmented Dickey-Fuller test. So let's do that. You once again go to view, unit root tests. Then I said you are testing these errors in levels at none. Then you click OK. You don't change anything else, click OK. What does this tell us? This is the Phillips-Perron method. What is it telling us?
It
The
is
null
stationary.
hypothesis ECT unit root. Yes, go on.
The stationary in levels at 1%.
Stationary levels at 1%. And what does that mean in terms of co-integration?
There is co-integration.
Correct, there is co-integration. So the variable ECT that we've created or that we've generated is stationary in levels at 1% level of significance. So there is co-integration. That is the interpretation you have to give to this. After interpreting the unit root, you have to go on and say there is co-integration amongst the variables that have been included in the long-run regression equation. Remember what we said earlier. These variables are individually non-stationary in levels, but collectively they are used to calculate the error term. We have collectively used them to calculate the error term, which means jointly these variables are now stationary in levels. If we are using the errors, they are now jointly stationary in levels, but individually they are not stationary in levels. I'm sure you still remember that. This is something that you need to understand for this course or even for the future, for those of you who do masters. But this doesn't change. It is what it is. So remember, we said our ECT lagged ones is equal to, according to what we have, is lean GDP, lagged ones is T minus 1. Minus, we had what? A beta 0 minus a beta 1, lean what? PCE, if you, a PCET, a minus what? Beta 2, lean PDI, minus beta 3, lean diff. So this is supposed to be T minus 1. This is also supposed to be T minus 1 because we are calculating the error correction term lagged ones. So all our variables are supposed to be lagged ones. I hope you can see. So all our variables are supposed to be lagged ones because we're calculating ECT lagged ones. So this is what we did. So from the test that we have done, we've established that these errors are stationary in levels. But where we started, we said all these variables, GDP, PCE, PDI, and dividend, are integrated of order 1. That is where we started. So individually, all the variables are integrated of order 1. But when we use them to calculate the error correction term, they become stationary in levels. So individually, they are non-stationary in levels, but collectively, through the error correction term, they are integrated of order 0, which means they are stationary in levels. And this is what gives us the information that the variables that have been included in the regression equation, GDP, PCE, PDI, and dividend, are co-integrated. So the co-integration part comes from the fact that even though individually they are non-stationary in levels, but collectively, through the error correction term, they are integrated of order 0. So it means they are co-integrated. In other words, they have a long-run economic relationship. And this is what allows us to specify and estimate the error correction model. All right. So let's repeat the test by using we have used the Phillips-Perron here, the Phillips-Perron. So let's repeat the test by using the augmented Dickey-Fuller test to see if the two tests confirm each other. So let's repeat the test. Also in levels, we now want the augmented Dickey-Fuller test at none, right? We repeat the test. What is it telling us? Almost the same result, that the errors are stationary in levels. So both the augmented Dickey-Fuller test and the Phillips-Perron test are confirming each other that the errors that we have generated from our long-run equation are stationary in levels, which means there is co-integration amongst the variables included in our long-run equation, which also means that there is a long-run economic relationship amongst the variables included in the long-run model, in our long-run model. I hope I have hammered that enough. We need to move on now. So this is what we need in order to specify and run the error correction model. So the error correction model that we need to specify, let me just write it down somewhere. The error correction model. So our error correction model is supposed to be something like this. I will write it here. I said the error correction model is to be specified in first differences or at the level at which the variables are stationary. We found that all our four variables are stationary after first differencing. So when we use them in our error correction model, they are supposed to be first differenced. So let's do that. So we have changing lean GDP, changing lean GDP, T is equal to, we used alpha in our long-run equation, is that so? So if we used alpha, then we use beta in the error correction model. So this is, did we use alpha or beta in the long-run equation? Please tell me we are still together.
We used alpha, sir.
Okay, if we use alpha, then let's use beta. So beta 0 plus beta 1, lean PCE T plus, this is our error correction equation, plus beta 2 lean PDI T plus beta 3 lean div T plus, or equation continuous, plus let me use another beta 4. This is the coefficient of the error correction term that we generated, ECT, but it's no longer ECT. The one that we used to test for cointegration is, we use ECT, right? So instead of using ECT, we need ECT lagged once. That is how we include it in our in our long run equation, ECT lagged once, plus a white noise error term, VT. Are we together?
Yes, sir.
Given the explanation that I've given you, which errors are we supposed to use to test for cointegration? Is it ECT or ECT minus 1? What is the logical thing to do given all the explanation that I've given you? What is the logical thing to do? Okay, fine. So this is ECT, the ECT that we calculated. To get ECT minus 1 is simply given by GDP lagged ones being explained by PCE lagged ones, GDP lagged ones minus PCE lagged ones minus the constant minus that equation that I erased. So for now, let's just stick to what I've shown you. This is enough. So this is our error correction equation, and we are saying this is the what? This is the constant. This is the constant. This is the short run parameter associated with PCE, short run parameter associated with PDI, short run parameter associated with dividend. This is the long run parameter, which is the coefficient of the error correction term. And this long run parameter gives us information about how GDP adjusts towards its long run equilibrium. It gives us information about how GDP adjusts towards its long run equilibrium. So I think you need to understand that as well. Now let's now go to our e-views and specify our error correction equation. And to specify our error correction equation, okay. You can save everything. You can, by just naming your equations, you can name them to save them. So this is equation 1, the long run equation. We've saved it. Now let's go to the next equation. Let's try to specify the next equation. So once again, I will right click here, open as equation, but there is some work that needs to be done here. There is some work that needs to be done. You put the constant after GDP, you put the constant there, but now we want to difference our variables. To difference our variables in e-views, to difference the variables, this is what you do. You simply write D, what? D GDP, GDP. This means the first difference of GDP. For PCE, it's D PCE, D PCE. This means the first difference of PCE. Same applies with the other two. You write them as D PDI, first difference of PDI, and your D dividend. D dividend, the first difference of the dividend. So this is how you difference your variables. Now, let's do that. To change the GDP to first difference, you just write D in brackets, GDP. That's the first difference of GDP. You go to the next one. You don't difference the constant, you leave it as it is. Then you go to D, PCE, D, PCE, the first difference of PCE, then the next one, D. So these are steps that you have to remember. Then D, dividend. the first difference of dividend. Right. So we have our model in differences. What else are we supposed to do? We are supposed to add the error correction term lagged once. Remember, we already generated our errors. They are here. These are the errors ECT. So we need to add the error correction term lagged once. It means that variable is lagged once. That variable is lagged once. Okay? So I hope you have understood that. I hope you have understood this. Just a moment, please. Just a moment. There's something that I need to sort out. Just a moment. I'll pause recording. Yeah, okay, I'm back. So this is our error correction equation. This is how we've specified it. This is the equation that we specified in our previous lecture, the one in red. And this is how you specify the equation in eViews. This is how you specify the equation in eViews. So fine. The method of estimation is least squares. So we go on and click OK and estimate our equation. So these are our results. I'm sure you can see our results. Look at this. The constant is not significant, right? Because its probability value is 14.85%. PCE is significantly explaining GDP at 1%. PDI is significantly explaining GDP at 1%. Dividend is not significant in explaining GDP at 1%. So it's explaining GDP at 32.97%. ECT is meeting the standards that we said. We said ECT is supposed to be negative and significant. So it's negative and significant at 1% in explaining GDP, which means the fact that we found that our variables are co-integrated by using that test that we did is being confirmed by this error correction term, which is negative and significant, signifying that our GDP variable adjusts towards its long-run equilibrium at the rate of 52% per annum, which means full equilibrium is attained in the second year, since we are using annual data. So this is the essence of that parameter. GDP adjusts towards its long-run equilibrium at 2% per year, meaning that full equilibrium is attained in the second year. Right? If you look at adjusted R squared, I want you to write this adjusted R squared down. I want you to write it down, 0.89. So write it in full, 0.89. We want to keep it and compare it with what we want to do later, 0.89, 3018. So that's our adjusted R squared. Adjusted R squared. Then the other thing of importance is the F statistic. What is it telling us? The model is good because the variables included in our regression equation are jointly influencing the dependent variable at 1% level of significance. So the model is good. If you look at the DW statistic, it's falling within 1.73 and 2.3, which means there is no autocorrelation. We have that, and we are going to confirm this by using the other tests that I said we can do. So that's fine. And the model that has been used to choose this estimated error correction model is the archaic information criterion, because it is the one with the smallest value of minus 6.887. So the archaic information criterion is the one that has been used to choose the model that has been estimated. So let's look at the significance. The standard errors, they are all okay, meaning that the model that has been estimated is efficient. It's an efficient model because the standard errors are small. We already talked about the significance of PCE and PDI. They are significant. The error correction term is also significant. Now, let's look at PCE. We are zeroing in on PCE. The variable PCE explains GDP in the short term, right? It explains GDP in the short term. In other words, we are saying in the short term, a 1% increase in the PCE will lead to a 0.70% increase in GDP in the short run. Ceteris paribus. Then if you go to PDI, a 1% increase in PDI will increase GDP by 0.81% in the short run, ceteris paribus. Then the dividend is not explaining GDP in the short run because its probability value is greater than 5%. Then the coefficient of ECT is a long run coefficient, right? Because ECT is the long run variable. So we've already said that GDP adjusts towards its long run equilibrium at the rate of 52% per annum. And full equilibrium is attained in this. So those are the interpretations you need to make of this result. That's it. So having said that, the next thing that I want us to do is to do the diagnostic tests. And at the end, don't forget to remind me to remove dividend and then see whether dividend is a redundant variable or a variable that we should keep in this model, right? So let's do the diagnostic tests. I click residual diagnostics. We are starting with the correlogram Q statistic. Remember, when we ran the long run model, the correlogram Q statistic was telling us that the model had autocorrelation. The residuals from the model had autocorrelation. So let's check to see if that is still the case after we have run the cointegration and the error correction model. Now, what is the difference here? Who can tell me the difference between the probability values for the correlogram that we ran after we did the long run model and what you are seeing now? What is the difference in the probability values?
All of them are more than 5%.
Yeah, all of them are more than 5%, meaning what? There is no
autocorrelation, sir.
There is no autocorrelation. So that's the conclusion you have to. So this test is one of the tests that you have to do when you are analyzing your own results. I urge you to do this test together with the Bruce-Godfrey LM test for autocorrelation. You do both tests and report your results. So the next test that we want to do is the Bruce-Godfrey test for serial autocorrelation. Bruce-Godfrey serial correlation test, this one. The null hypothesis is given here. There is no need for you to even remember. If the results are displayed, the null hypothesis is no serial correlation up to 2 lags. That is what it is telling us. No serial correlation up to 2 lags. But according to the correlogram that we just saw, no serial correlation up to the 16th lag. There is no serial correlation. So, what is our conclusion here? The hypothesis, you now know them. There's no need for me to keep on repeating them. I just want the conclusion.
So we fail to reject the null hypothesis, meaning that there is
Meaning
no
what?
serial
Correct.
correlation.
There is no serial correlation. So both the tests are telling us that there is no serial correlation. Now we go to the next test, normality. What is there? Normality. Who can interpret that test? Please give me the answer.
The residuals are normally distributed.
Yeah?
The residuals
Yes.
are normally distributed.
That is not true.
It's not
If you
true.
look at the probability, look at the
1%.
probability. Yeah? What is the decision rule?
So it's less than 0.05%. So we so we don't reject the null hypothesis.
No. We rejected the null hypothesis. Because we said we fail to reject the null hypothesis if the probability is greater than 5%.
Okay, yes.
This one is greater than 5%.
Okay, yes.
So we don't fail to reject the null hypothesis, which means we reject it
Okay.
and accept the alternative. So this is the downside of this result. The normality is not right. Let's go to the next test. Let's go to the next test, heteroscedasticity. I'm going to choose the arch test. What is it telling us? Now hypothesis is homoscedasticity, alternative heteroscedasticity. What is the conclusion? The residuals are
Homoscedastic, sir.
homoscedastic, yes. Then are homoscedastic because the p-values are all greater than 5%. Then we can do a third heteroscedasticity test. A third heteroscedasticity test. Let's do the Harvey test. And all of them are confirming each other that there is homoscedasticity. Let's go to a stability test, Rams reset. Click OK, Rams reset. What is it telling us? The model is correctly specified. With the p-values for the F-test is greater than 5%. Correctly specified. Then let's go on. Another stability test, recursive. This one, the blue line lies within the 95% confidence interval, meaning that the parameters in the estimated regression equation are stable, which is what we want. We repeat the test using the Kusum of squares test.
Kusum.
Of squares test. This one is telling us that there is some instability here. So the two Kusum tests are not confirming each other. So what problems do we have with this model? There are two problems. One problem is the normality, which is not right. The second problem is the Kusum of squares test. Otherwise, all the other tests are fine. Now, having said that,
Is it clear?
we've taken note of the coefficient of dividend. Right, coefficient of dividend. Now, the next thing that I want us to do, we are going to remove dividend. We are going to remove dividend from this model. Take note to what happens to our adjusted R squared. Our adjusted R squared is 0.893018, which I said write it down. After removing that variable, can you see what has happened now? What has happened to our adjusted R squared? Who can tell me?
It increased, sir.
Increased, sir.
Adjusted R squared is increased. What this means is that variable dividend was a superfluous variable, it was a redundant variable. So we need to drop it out of this regression equation completely. We need to remove it from our regression equation completely. So what I've done here, I've actually taken a shortcut. So let's look at these results and see if there is any improvement that we witness on these results. If we don't get good results, we will start over quickly. Let's see if the results improved. F statistic is still fine. DW is lying within the range. R squared is increased. Right? Then PCE is positively related to GDP. PDI positively related to GDP. Our error correction term is negative and significant. It's not very different from the error correction coefficient that we had previously. It's not very different. It's more or less the same. Now, if you also compare these coefficients, they are supposed to be smaller than the long-run coefficients that we found on that long-run equation. They are supposed to be smaller. Then let's quickly do our diagnostic tests again to see if there is any improvement that we can witness. Let's do the parallelogram Q-squared test. Any change? No change. There is no autocorrelation from this test. Let's do the test using the serial Bruch-Godfrey test. Bruch-Godfrey serial LM test is also showing us that there is no autocorrelation because the p-values are greater than 5%. So that test is fine. Let's go to the next test, normality. Still a problem. There's still a problem of normality. I'm sure you can see that. Let's go on. Normality is still a problem. Let's go to heteroscedasticity. There's a reason why these results are not right. We'll resolve the problem before the end of the lecture. Heteroscedasticity, there is no heteroscedasticity, but the p-values are greater than 5%. So that's fine. I'll just do one test now. Let's go to Ram's reset. Ram's reset is telling us that using the F-test that the model is correctly specified because p-value is greater than 5%. Let's go to the stability test, the Kusum and the Kusum of squares. It's fine. It's lying within the bounds. What about the cusum of squares? Is it still giving us problems? Cusum of squares? Yes, it's still giving us problems. In equation 2. So I've saved it as equation 2. All right. Let's redo this. Let's redo this. We are now going to estimate a model with the GDP, PCE, and PDI. These three only. Estimate the long run equation. This is the long run equation. We are going to generate the errors from this long run equation. This will be quick. We make the residuals and we call them ECT. ECT1. We've called them ECT1 to differentiate them from the first ECTs that we generated. So these are our ECT. We test these for unit roots using the augmented Dickey Fuller at none, in levels at none. Test them. You can see that there is cointegration at 1% level of significance, which means we can specify an error correction model for these variables. Fine. We are done with that. Let me name this equation 3. So next, I specify the error correction equation. I'm now moving very fast because it's something that we've done. So what do we do here? We difference our variables. Difference our variables. Difference our variables. D. Then we add the ECT1 lagged ones minus 1 lagged ones. So we have our equation is now complete. Click OK. These are our results. And you can see even the coefficient of the constant is now significant. The previous result that we had, this one, the constant, yeah, was also significant. No, these are the long run results. These are the results. Okay, well, it's fine. Let's leave it at that. Right, so these are our results, and you can see the results have improved because everything is now significantly explaining the dependent variable. Our adjusted R squared is that our DW is within the bounds between 1.7 and 2.3. Our F statistic is okay, fine. So let's try to see if the diagnostic tests have improved in this new model that we have. Diagnostic tests, the Q statistic, no autocorrelation. It's showing there's no autocorrelation. We go to the next test, serial correlation. It's also showing that there's no autocorrelation. The p-values are greater than 5%. We repeat the test. We do the normality test. It's now 0.06. There's still a normality problem. Yeah, so maybe this is a problem with the data that we have used. There's still a normality problem, which means if we do those other two tests, the
square.
The cusum of squares test. Let's just do the cusum of squares. It's still giving us problems. So the challenge that we have here is a data-related problem. It's a data-related problem. Now, let me go to the data that I gave you last time. The data that we used last time, and see if there's any improvement that we get. This is the last exercise that we are doing. So these challenges that we are facing now are the very same challenges that you will face when you are doing your research projects in the second semester. You will encounter something like this. So it's normal. It's normal. So I will stop the share. and then share my if views again. I want to share the if views. Stop this share. I want to share my views again. Yes, this is the if views. All right. So what I want to do is to go to the data that we used last time. I will save this. Right. Are you seeing my if views?
Yes, sir.
Okay, I'm to the data that we used last time. I'm sure it's this one. Right. This is the data that we used last time. I hope this one will behave in the normal way. I will pick the three variables that we used last. GDP, we need to convert them to what? We need to convert them to logs first. So we need our lean GDP is equal to log. This is the last exercise we are doing, log GDP. Right, then that's that. Then we also need a lean PCE. Lean PCE is equal to log PCE. Then the third one is PDI. Lean PDI is equal to log PDI. PDI. Right, so we are assuming that our variables are integrated of order 1, all of them. They are integrated of order 1. Right, so let's estimate the long run equation. Long run equation is PCE and PDI. So let's open as equation. This is our long run equation, right? I'm not changing anything. This is our long run equation. And I'm going to name it. It's equation 3. Our long run equation is equation 3. Maybe what I can do here is to delete equation 1 and 2. Delete equation 1 and 2 so that we don't mix up things. And I will call this one, I will rename it. You can rename it to equation 1. So that we start our counting from 1. Click OK. It's now named equation 1. That's our equation that we just estimated. It's equation 1. That is the equation that we just estimated. Now, using this equation, we are going to generate our errors, make residuals, and I'm going to call the errors ECT. I'll call the errors ECT. And we replace the ECT variable. So we've called them ECT. Now we quickly test them for cointegration, just like we did with the other one. You go to make residuals. You go to view. You go to proc. Can you see where there is what make residuals? What's happening here? Proc. Okay, let me start over again. Right, so I am saying we've already made residuals, make residuals. It's ECT. We already did that. So we replace the existing one. Fine. So we are testing this one for cointegration. So it's unit root standard. It's none. Click that. It means there is cointegration at 1% level here. That is our conclusion, which means we can specify and estimate our error correction equation. So this is fine. There's no problem here. Right. So the next thing that we do is to, I will name this equation 1, minimize. Now we go to our variables once again, GDP, PCE, and PDI. We want to specify the error correction equation now. So for the error correction equation, I'm putting my C at the right place, C there. We difference our variables. I just want to see if we get different results. We difference our variables. All our variables, we difference them. Difference them and remove the C at the end. Then our ECT is supposed to be lagged once. It's supposed to be lagged once. We have our complete model. I'm sure you can see we have our complete model. Then you estimate this equation. It's saying ECT is not defined. Why is it not defined? Didn't we generate ECT?
You should put ECT 1.
No. Just a moment. You said I put ECT 1. I didn't do that. Did we generate it? Did we save it? I know we tested it for cointegration. So it means we have to go back to the results in equation 1. Let me see. Work file. Right. So I will go to the results in equation 1. These are our long run results. Then we make residuals. Maybe we did not save ECT. Right. We are not calling it 1 because there is no other ECT there. So click OK. We have that. This is what we use to test for cointegration. And we found that there is cointegration. So we did not save it initially. I will name this one ECT. So it's fine. We now have it. So the next thing that we do is to specify the long run equation. So let's do our long run equation. Open that. So let's write our error correction equation. See that we difference our variables D. This is important. What we are doing is very important. Pay attention, please, because there is something that is going to change. Then another D. Another D. Then we have ECT, lagged once, -1. Right. So we now have a complete model, our error correction equation. Click that. These are our results. As you can see, the constant is significant at 10%, PCE significant at 1%, PDI at 1%. The error correction term significant at 1% as well. Our DW is okay. Our F statistic is okay. Adjusted R squared is okay. Fine. Now we want to quickly do our diagnostic test again. Pay attention, something may change here. Right. So we do our Q statistics. It's showing that there is no autocorrelation, because the p-values are all greater than 5%. We repeat the autocorrelation test by using the Bruch-Godfrey test. It's also showing us that there is no autocorrelation. I'm sure you can see it. No autocorrelation, because the p-values are greater than 5%. Then we do our normality test. Yeah, still there is a problem. So maybe let's leave this. What I'm going to do is next time I will give you data that I will have tested, how it behaves. So next time when we do our tutorial for the next chapter, we are going to start off by estimating a model whose results will show all our diagnostic tests to be good. That is the model that we'll do before we look at the next what? Before we look at the tutorial for the next chapter. But the steps that we have taken to do our estimations are all the steps that you should follow when you are doing your cointegration and error correction modeling. So you must remember what we said at the beginning, that before you estimate an error correction model, the first thing that you do is to test your variables for unit roots. And all your variables are supposed to be integrated of order 1. After that, you estimate your long-run equation. And then from the long-run equation, you generate the errors and use those errors to test for co-integration by running the unit root test, using the augmented Dick-Fuller test and the Phillips-Perron equation, where you use a model without a constant and a trend. If the errors are significant in levels, then that is what confirms that there is co-integration. And that is what allows you to specify and estimate an error correction model. And the way in which you specify and estimate an error correction model is the way that we've been doing it, even though the data that I've used has some problems which are being picked when we do the diagnostic tests. So those are the steps that you follow when using co-integration and error correction modeling. So there is nothing wrong with everything that we have done today. Everything is perfect. The only thing is that the data that we've used is the one that is problematic. So if you are doing your own study, this is the stage where you have to go back to the drawing board, try to collect better data, right? And then test it again. If it gives you good results, then you proceed. If it doesn't give you good results, you have to find good data that you can use in your estimations. So with that, we come to the end of our tutorial. The next time we meet, we are going to meet face-to-face. And we are going to discuss the next chapter. Okay, so see you next time.
Thank you, sir.
Bye, sir.
Thank you.
See you.